Hello everyone, welcome to our talk, Performance Consistency in the Cloud. I'm Sercan, a Principal Solutions Architect in AWS, and today I'm here with my colleague Nati.
So my name is Nati Cohen, I'm a Specialist Solutions Architect in AWS for Compute.
Yeah, so while most applications handle latency variations just fine, there's a growing set of applications where consistency is as important as speed itself. So that's why we are here today. I want you to, for a moment, imagine a scenario where you work for a high-frequency trading company and managing, let's say, a Redis cluster. And that cluster, let's say, processes thousands of messages per second. And every microsecond matters in this context because it's a trading. And one day, without any code change, nothing changes, no production rollout, nothing at all, your latency spikes from 50 microseconds to, let's say, 200 microseconds. Just for, let's say, 100 milliseconds. And that brief spikes in this industry usually cost you $1 million in missed opportunities. In fact, this isn't a hypothetical scenario. It's the reality of performance-critical applications. Who here has experienced unexplained performance variations in the cloud? Keep your hands up, please. Nice. So for you guys, this is going to be particularly important. But for others, it hopefully will help you get some intuition how things work behind the scene. Now that I hope that I got your attention, let's look at what happens under the hood. Performance variation, what it is it's also called jitter, is the consistency, is the inconsistency in response times for identical operations. In a perfect world, if an operation takes 50 microseconds, it would always take 50 microseconds, no matter what. But the reality is sometimes an operation takes 30 microseconds, sometimes 500 microseconds. And here is the kicker. This happens without any change, no reason in your code, no increase in the load, no obvious reason. Imagine, let's put it this way. You are driving to work from your home, and it takes 30 minutes. But sometimes no traffic, no construction work, no weather issues, it takes 2 hours. How can we explain this? You probably would find a new route. It cannot be the same route. So, in fact, in the cloud, we accept this level of unpredictability. However, I want to be absolutely clear here because I'm not saying everyone needs to obsess over microsecond level consistency. Let's say you are running a content management system, SaaS application, e-commerce platform. You probably have a bigger fish to fry. And that's perfectly fine. For most applications, this variation gets absorbed in the noise. Your web server, let's say, is taking a few more milliseconds than it's supposed to be. Nobody notices. Your users won't notice it, so who cares? But when you're processing thousands of requests per second, then it becomes an issue. The variation becomes your biggest enemy. Particularly high-frequency trading, gaming and multimedia, and when you perform benchmarks, that's absolutely critical. In this, for example, high-frequency trading, usually in this world, worst-case latency matters more than average latency. You know why? Because if you can't guarantee an order is going to reach to an exchange within a specific time period, that's a lost opportunity. And I often hear this term from my customers. It's not about being fastest, but it's about never being too slow. So they want to be very predictable at, let's say, P99, P99.9 percentiles. For one of my customers, I was able to help them to cut tail latency by 100 microseconds. And that sounds not so important, but for them, this was millions of dollars revenue annually. Another example is gamers, maybe. Let's say a game running at 60 FPS, and then for 100 milliseconds, it drops to 30 FPS. What does it mean? It's probably a missed headshot or crashed race car, right? So it's also important for this type of customers. Also, let's say you are running a performance benchmark. For example, I was helping one of our customers improving their code. They spent weeks of engineering time, and they were able to reduce their latencies by 50%, but all of a sudden they were hitting CDN limits. So it's important to know limits as well. Now that we understand why this is important, but even if you are not in these industries, like I said, it's still relevant for you. So, you might have heard this term, cloud is someone else's computer, but actually it's a little bit more complex than that, even though I'm happy that it feels this way. So we actually add layers and layers on top of inherently complex system. And also we add these layers, but also we share on top of these layers. So we are not just dealing with a complex system, but we simplify it for customers, and we take care of the rest. So your application, for example, runs on a virtual machine, and that virtual machine shares a physical hardware, CPU, network interfaces, memory with other virtual machines. That's sharing layer 1. And the virtual machine is an abstraction layer. So we share that. On top of that, you have your local storage, which is supposed to be local, but it's actually accessed over a network. So your storage is another abstraction. And we share that as well, because the network, underlying network, is shared with thousands of other workloads. And each layer adds a variation. And it's just not additive, but actually it's multiplicative. Each layer, each sharing multiplies this variation. And in this talk, we will talk about underlying layer because it's a shared responsibility model. You manage your application and operating system, we manage the rest. And then we will talk about where this variation comes from. So we identify 4 different areas: VM multi-tenancy, CPU, storage, and network connectivity. All right, if you take away one thing from this talk, it could be this slide, because VM multi-tenancy is one of the biggest culprit in performance variation, because when you run multiple virtual machines on the same physical host, they are not just sharing a space, they are actually actively competing for resources. Now, here is what many people don't realize. Cloud providers actually implements limits to make it fair for all the tenants. It's like, let's say, having a traffic lights at the intersection. And imagine doing that also would require a compute power. But for that, AWS has Nitro, so we don't actually use customer CPUs for managing these. We offload this to Nitro layer. So imagine you rent a house, but for some period of time, your landlord comes in and stays with you for a few days. It's like that. But we don't do that. We offload this capability to Nitro engine. And the existence of this limit is usually documented. Like if you go to AWS documentation, somewhere in the page 950, you'll find all these limits. And we actually read these documentations. That's our 24/7 job. But it's often hard to find actual thresholds, the resolutions, mitigations. So those are not always clear. So today, I'm here with my colleague, Nati. He's going to talk about all these limits and then how to mitigate them.
Thank you. So now that we understand in which situations we do care about performance variation, let's talk about the sources for performance variation and how you can mitigate them in a cloud environment. And so, as it was mentioned, in a lot of places where we can, we add limits to enable fairness. So it's pretty important in some workloads to understand what these limits are. And in some cases, if you want to mitigate that, or if you want to avoid variance due to limits, and some of these limits can be static and some of these limits can be burstable, right? So you can actively choose the instances that you're running on. So for example, if you want to avoid CPU bursting limits, you can run on instances that don't have them, right? If you want more or higher limits, you can use larger instances for your workload. And for some of these limits, you can just walk around them. So for example, there are limits around the amount of connection tracking that we can do, but you can use untracked connections, right? And there is, of course, a trade-off, but this is something that some customers choose to do. Or if there are limits around the amount of DNS queries that you can do, you can always cache your DNS. In your instances in AWS, by the way, there is a mechanism called instance bandwidth configuration where you can say, I need, for this specific workload, more bandwidth toward my network, and I can take less bandwidth toward my block storage, right? Or the other way around. There are some resources where we can't enforce limits, and so these are shared resources. For example, when there are multiple tenants using the same CPU sockets, they all share the same L3 cache. When there are multiple tenants that share the same SSD device, they share the same SSD cache. When there are multiple workloads sharing a specific host, they are sharing the bus between the memory and the CPU. And when there are multiple tenants using the same CPU socket, they share the same thermal and power management limits, right? So if one of them creates more thermal load on the socket, in x86 CPUs, usually it means the frequency is going to drop for everyone on that socket. As also was mentioned, if we're all using the same hypervisor, steal time is also something that's being shared among the tenants. And for some of these things, these are things that the cloud providers take and try to minimize. So for example, for hypervisor steal time, since almost 10 years ago, we introduced the Nitro hypervisor, which push a lot of the work to hardware. And then it minimizes the steal time. And we had this blog post published showing multiple different HPC workloads are suffering less than 1% of difference when running with an hypervisor and without an hypervisor. For L3 cache and memory bus, customers can take larger instances and then occupy an entire CPU socket, and then they are not impacted by other customers. Or they can take a dedicated host and then they can choose their neighbors, right? Or choose no neighbors. In terms of CPU, so we mostly talked about that. You can choose to be on your own CPU socket. You don't have to take the entire host. And this usually solves things like thermal limit, drops of frequency or power drops of frequency, or it also allows you to configure things like your idle state and power state, and so prevent the CPU from going to sleep and then dropping frequency. If consistency is more important to you than speed or single thread performance, you can so opt to use fixed frequency CPUs. So at least on AWS, all the ARM64 CPUs have fixed frequency. So if predictability is more important than speed of a single thread, you can choose to use that. And of course, we highly recommend to monitor these frequency changes, because you might find out that if you have performance drops, this is not the place that you should be looking at, and you should be looking actually at somewhere else. In terms of storage, some variability comes from managed block storage. So managed block storage might look to new customers of the cloud like a local disk, right? You see an NVMe device. But in practice, this is a block device that is being given to you behind some network and from a larger system. And so in order to get from your host to that system, we need to take the network. Some of the paths may be longer, some of the paths might be congested. It usually offers different volume types. Each of these volume types have different variance options, or profile, more correctly to say. And also that large system can have maintenance events. So you might feel these as performance spike. Most customers, again, have these every day and don't feel them. But if you're in the situation where performance variance is matter to you, then this is something you might feel. And again, there are limits both on the instance side and on the volume side. So be aware to these, work around, again, with the limits, with the volume type, and maybe prefer local attached SSD where you can. And on the AWS side, we do something called SRD. So we are connecting to the storage over multiple paths, and so we are able to avoid congested paths and improve tail latency, and you can read that in that paper. This is a great blog from Percona. They tested multiple different volume types, specifically on EBS, and showed different variability. I think that if this is something you care about and you use EBS in your workload, you should probably consider doing a similar test to choose the volume you're running on. You can also choose to use local SSDs. So these will have less variance. These are SSDs that are connected directly to your host, but with the trade-off of being ephemeral, right? When the host goes away, they go away. Over there, you should note that smaller instances tend to share a single SSD device, so they share the SSD cache. So if this is a problem for you, you can opt to use instance of a size that gets a full disk. There are, again, limits of IOPS and throughput implemented on the controller, but recently we also introduced ways to monitor them. So you will know if this is something you are hitting or not. And operating at a scale of AWS, we found that when we use SSDs from lots of providers, different SSD controllers on the disks themselves have different performance profile, specifically around tail latency. And so what we did is we decided to build one ourselves. And we reduce tail latency for all of our SSDs. Also consider using newer instances which have this Nitro SSD controller, and then you will get reduced variability for free. In terms of network connectivity, and this is the last part that we're going to discuss today. Your instances are placed on the data center, and they can take a different network path between themselves based on the flow. And some of these paths might be longer than others. Some of these paths might be congested. If you are deploying in multiple availability zones, so in multiple data centers, we are adding more hops, so more options for paths that can be longer or congested. And then to add on top of that, placement is by default implicit, right? So even if you launch two instances, by default, they can be in the same rack or be in different places in the data center. And there are also mitigations against that. So on AWS, you can use something called placement group, and then you request to launch instances into the same network spine, which can help reduce latency. If you can't do that, for example, you want reduced latency against someone else's VM, you can engage in a practice called latency hunting. So you will launch different instances and try to find the one with the shortest latency. And again, there are things that we are doing on our side. And you can choose instances that we provision on the same, on closer together in the data center. To summarize, for most of you, you can live with latency variance perfectly fine. But for those of you who need more consistency, remember that each layer adds some latency variation, but there are mitigations that you can take, and they have trade-offs. Thank you so much, and we'll take the questions on Slack.